velocity. And the linear momentum actually for this rigid body is given by the summation of mass of each particles on the rigid body times the average velocity plus the relative velocity. And for each part of this right hand equation, so we can represent the linear momentum for the whole body equal to the average velocity times the summation of mass of that body. And for the second part in the bracket, we have the velocity, the cross product of angular velocity times the summation of mass times the relative position rho I. Actually, for rigid body is equal to 0. So the summation of forces, which is given by the uh, time rate of change of linear momentum, can be written for a period of time as in equation 612, right? So we have a initial linear momentum plus the total linear impulse equal to the final uh, linear momentum of the rigid body. And since this vector is a vector quantity, we can write the equation. So we can see that we have only two components here because for the rigid body, it has only x and y component. And then we can expand that in terms of linear impulse momentum equations, equation 612 in x and y component. Now we look at how to derive the angular momentum for rigid body, right? So we start with the fundamental first. So angular momentum, as we mentioned here before, is given by the symbol H, and we are looking at the angular momentum about the mass center. So that is defined by the relative position times the cross product with the linear momentum at each locations. So the angular momentum about the mass center actually is a summation of moment by all linear momentum, linear momenta, because momenta means a plurals of momentum, right, of all particles. Right. So here I'm repeating what I've said before. Here we look at the individual mass inside the rigid body, and here we want to calculate the moment, the angular momentum of the rigid body about its mass center is equal to the moment of inertias about the mass center times the angular speed of the rigid body. So this actually, because we are considered only a plane motion, actually in the vertical plane. So this equation 613 will be used throughout the topics. And in order for us to find the moment about the mass center for the rigid body, this one is equal to time rate um, change of the angular momentum about the mass center. So we have the summation of all moments about the mass center when we know about the forces acting in the body. This one equal to the right time rate of change of angular momentum of that rigid body about the mass center. And when we rearrange the equation that we had before in order for us to use the angular impulse uh, equations, we we rewrite in terms of the angular impulse and get total um, angular impulse, and we try to relate it with the angular momentum of the body. So when we look at the particle, we have what we call impulse momentum diagram. For rigid body, also we have that kind of concept. So Professor Merriam here show us the what we call the momentum diagram. So this momentum diagram is used to help us to understand about the effect of the um, angular momentum to the motion of the rigid body. And this diagram applied for general plane motion, translation, or with the rotational effect. So when we look at the cases, when we want to know about the angular momentum about O, which is not the mass centers, we have the equation 615. We have the angular momentum of the rigid body about the mass center plus the mass of the rigid body times the translational speed of the rigid body time the distance normal to the velocity vectors, right? So as mentioned there, this expression hold at any particular instant of time about the O that we determine, and this expression hold for the body which is fixed or moving uh, uh, in the motion I mentioned earlier. Right. So the the left figure here relate to the pure rotational motion. In the pure rotational motion, the rigid body rotates about a fixed point on the body. Here, the average velocity is given by the distance from the mass center to the fixed point, axis of rotation, given by the R over bar, and the average velocity here tells us that um, the linear velocity of the mass center is given by the overbar, the distance from the fixed point to the angular speed of the rigid body. So the linear momentums, the angular momentums about the fixed from the axis of rotation is given by the moment of inertia uh, about the mass center times the angular speed plus the mass times the distance power of 2 from the fixed point times the angular speed. So we obtain the moment of inertials of the rigid body about the fixed point. And similarly, we can obtain the angular, we can express again the angular momentum of the rigid body about the fixed point uh, by the equation 16. The moment angular momentum equation about the fixed point uh, for the rigid body moving in the vertical plane is given by the summation of all moment about the fixed point equal to rate of change of angular momentum about the fixed point. And by looking at the angular impulse, if we multiply these equations, um, we obtain the 617, equation 617. So that will be the moment angular momentum equation about the fixed point. Now we can look at the conservation of momentum for the rigid body. So it says here the principle of conservation of angular momentum for a single body or a rigid body that is connected. If the summation of force or the net force is zero for a given interval of time, so the linear momentums at the initial and the final time will be equals. So the linear momentum vectors and does not change if there is no linear impulse. When we talk about the angular motions, if the resultant moment about a fixed point, or this for pure rotation, or when we have a general plane motion, if the resultant moment is zero for interval of time, the angular momentum for the pure rotation and the angular momentum for general plane motion um, will be conserved if the angular impulse is zero. Here I place the tips by the Professor Merriam for system of interconnected rigid bodies. Um, there may be linear momentum changes of individual parts um, of the system. I mean the connected rigid bodies during the interval when the force is applied or the moment being applied, but there will be no resultant momentum change for the whole system if there is no linear impulse. The impulse means the force times the time that the force being applied to the rigid bodies. Similarly, if there may be angular momentum changes of individual rigid bodies during the interval, but there will be no resultant angular momentum change for the rigid bodies as a whole if the angular impulse about a fixed point is absent. In solving the problems, the center of mass for the system is generally is not convenient to be used. So these are the tips by the Professor Merriam when we are solving the interconnected bodies.